Hi everyone, welcome to my channel and welcome to this video. So what I've been wondering for some days now is I haven't really used a linked list data structure in some time. I mean the last time I used was to handle bullets while implementing space invaders for my handheld console Mono Retro, which has been built from scratch. And to be honest, that was like using linked list for the first time in several years after coming out of my university. I kind of like linked list as a data structure. It's simple, effective, and perhaps one of the most important data structure which often acts as a base for other data structures. Also, for most of us CS students, linked list I believe is the first intermediate level data structure that we learn after the basic ones, that is arrays and pointers. So I've been thinking what else I can build which will have a nice application of linked list. I mean, I could always go to LeetCode or any other such website and start solving linked list related problems. But that's like a pseudo use of linked list. I'm not really building anything interesting. Now, the other thing that I've also been into recently is memory allocators or dynamic memory allocators and how they work on Linux. What are the different approaches present? How does something like malloc work on Linux and things like that? And while doing so, I realized there is a pretty cool way to use linked list while designing a memory allocator. In fact, a linked list is often the core data structure used to design a memory allocator. I mean, of course, there are other advanced approaches which uses things like red black trees, etc. But that's for another day. Once I came to know about this, I was like, I need to implement a memory allocator myself and see how it works. So here I am doing this video where we are going to create a very simple memory allocator, pretty much like a simpler version of malloc on Linux, and try to understand how dynamic memory allocation works, how new heap memory can be requested from OS, how we can implement our own free, the function to free allocated memory, and some of the approaches that exists which allow us to create a memory allocator. Yep, so that's what we are going to do in this video, and as always, let's get started. Okay, so before going to the actual coding part, or before we begin creating our memory allocator, let's try to understand what or how actually dynamic memory allocation works in Linux. How we can actually request unmapped memory region from the OS and map it to the process memory. Okay, so for that, let's try to understand the process memory footprint, or how the memory layout of a process looks like. So let us consider this is the memory layout of a process. The memory locations are increasing upward. So first we have our code section. So this is actually where your program code, the text section or the program code resides. This is basically where your ELF code resides. Then comes data section, where your initialized variables and constants lie in your program. Then comes BSS, where your uninitialized variables lie. That is the variables for which space has been allocated, but they have not been initialized yet. So that is the BSS section, like your arrays and those kind of things. That remains in the BSS section. And then comes the heap. Let's say this much heap is already allocated by the by your process, and here we have the stack. So the stack grows downwards and the heap grows upwards, and this entire region is basically unallocated. This is unallocated memory area. So this is the area from where we can request memory blocks from the OS. The process can request more memory from the OS, and the OS will allocate that memory, that requested amount of memory, from this unallocated area. So how does this request work? So how can a process request a memory from the operating system? So on Linux, we have this very useful system call called sbrk. This is the system call using which a process can ask for additional memory, unmapped memory from the operating system, and it will be allocated from this unallocated region. So what does sbrk do? It changes the program break of the process. So basically it changes the location of the allocated memory region of the process. So right now, let's say this is the location. This is the memory location where the allocated memory region of this process ends. The allocated heap memory region of this process ends. Or in other words, this is the program break right now. This location, let's call it 0x20. This is where the program break of this process is located. So what sbrk will do is it will change the program break for this process. Increasing the program break has the effect of allocating more memory area, and decreasing the program break has the effect of deallocating memory area or mapped memory space. And how sbrk works is we call sbrk with an integer. Let's say I call it with 4. So what sbrk will do is it will change the program break to 200 plus 4, that is 0x204. So these are in bytes, right? So I'm basically requesting 4 bytes of memory or a 4 byte memory block. So it will basically change the program break to 0x204, and it will return a pointer to the beginning of this newly mapped memory space. This is the newly mapped memory region. And so what sbrk did is it added 4 more bytes to the allocated area. So it changed the program break from 0x200 to 0x204, and so this is the current program break, and it will return a pointer. So it will return this address. It will return a pointer to the start of this newly allocated memory region, that is this address 0x200. So that's how we can allocate more memories from the operating system, or we can request more memory from the operating system to be allocated to a process. Now, to design our memory allocator, that is a simpler version of malloc, something which we can very naively do is we can simply make our version of malloc. Let's call it Ymalloc. So I'll be calling my version of malloc Ymalloc. There are various versions of mallocs, like there is Zmalloc, there is Dmalloc, there is Fmalloc. So many mallocs are there. So I have chosen the letter Y for my version of malloc. So what Ymalloc will do, what Ymalloc can do, one of the approaches that Ymalloc can take, it's simply it can act as a wrapper for sbrk. Whenever I do Ymalloc, let's say 10, what Ymalloc will do is it will simply call sbrk with the same size, that is 10, and it whatever the address or to the pointer that it returns, it simply proxies it back to the calling function, right? So that is one thing that one Ymalloc can do, and the calling function can then cast this pointer to the required data type. So this is like the most naive implementation of Ymalloc that we can do. However, what is the problem that we can face if we follow this procedure? If we keep on using sbrk to request more and more memory from the operating system, soon we would run out of memory and our program will crash. And especially if we are using something like a C group or something to limit memory access, or to limit memory access beyond a certain limit or a certain value, like our program is bound to fail or bound to crash, because we would just keep on requesting more and more memory from the operating system without reusing the already allocated blocks, right? So one interesting thing to note about this is that if we call sbrk with negative value, it kind of reduces the program break, which means it deallocates the allocated area. So let's say if I do a sbrk -2 at this point, it should reduce the program break to 0x202. That is one way to deallocate memory. But the problem is, let's say we have right now allocated something like, so let's say our program break is somewhere over here. This is where our program break is located, and somehow let's say we have allocated 4 blocks of 4 byte memories. So this is a 4 byte memory, 4 byte memory, 4 byte memory, 4 byte memory, right? And all of these are allocated right now. They contain data, and somehow this block we don't require it anymore, and so we can call sbrk with -4, and it will move the pointer back here, and this block will be gone, right? However, let's say this is a block that has been freed, so we need to free this block. We don't need this data anymore. Now this is something which we can't do, because doing a sbrk -4 will always work this way from this edge of the program break. sbrk will always work with the program break, so it can move this way, but we cannot randomly reallocate a block which is allocated in the middle of our allocated region. So that's why we can't use sbrk negative value all the time. So we need to come up with our own mechanism to reuse allocated blocks when the data stored at some block is no more required. We need to figure out a mechanism to reuse already existing allocated blocks. Okay, so now that we know what is the limitation of using sbrk for memory allocation and deallocation to some extent, next we need to figure out what strategies we can use to reuse or an already allocated block when the data residing in it is of no use anymore. how we can randomly allocate and deallocate the memory blocks. So there are quite a few strategies to do that, but we'll be implementing two of the simplest strategies. This brings us to dynamic allocation. This allocation and reallocation and reuse of existing blocks, that's nothing but dynamic allocation of memory by a process. And so yeah, let's see how that works and what are the different mechanisms. Let me make some space. So the most basic things that we need to implement in order to implement our allocator is a way to track what memory blocks are allocated and what memory blocks are in use and which ones are not in use. And then we need to devise a mechanism to find a block which can be reused and which solves our purpose, or which satisfies the amount of memory we require, right? So one approach that we can do is we can maintain a pool of the process itself can maintain a pool of memory blocks. Now here there are again different strategies. It can be, we can separate the pool of used blocks and the pool of unused memory blocks, or memory blocks which are ready to be freed, or we can maintain a single pool of memory, and we can somehow mark whether a block is in use or a block is out of use. So let's start simple and see what we can do. So once again, let us consider that this is the unallocated area, and whenever we need memory and we don't have any blocks, current memory blocks with the process will request some memory block from the OS. So let's say right now nothing is allocated. So what happens now is, let's say the process has just started, and at this point of time the process's memory pool is completely empty, there is nothing in it. Just an example. So the processor's own memory pool is empty, and at this point of time what the process wants to do is it wants to allocate some memory using Ymalloc. So what Ymalloc sees is that there is no allocated memory yet, so it asks the OS to get some memory space allocated using sbrk. Let's say it needs 4 bytes, right? So what happens now, the process gets back 4 bytes and it's in use. So we will denote whether a block is free or not, let's say by this flag f. So in this case f, since the process has requested for this memory, what Ymalloc will do is it will acquire that memory and it will mark that it's in use. We will use a f flag and we will say that it is in use, so it is not free. So f equal to 0 means it's not free, it's in use. So f simply stands for free. And then what happens, let's say its position, the memory address of this is 0x200. So now let's say this 200th block, the 200 memory block is full, and the process needs another 4 bytes. What Ymalloc does is Ymalloc checks that right now in its pool it has got no free space or no free block. So what it does is it once again asks sbrk to return another 4 bytes of memory block. So what happens is that, so sbrk returns another 4 bytes of memory. Now we have another memory block. So we have another memory block, and again it's in use. Now what happens is, and let's say we allocate another 2 byte block, another 8 byte block, and so on. And now what the process decides is that it says that it doesn't need this 4 byte block anymore. So in usual case there is always a function in C which is called free, a library call, and we always pass a pointer to a memory address over here. And what free does, it frees this memory pointer. So what actually happens is that in this case what free will actually do is that it will mark this as 1, which means this block is now freed. Also let's label these starting addresses of these blocks nicely. I'll just use their decimal addresses for now. Let's call it 100, let's call it 104 since it's 4 bytes, 108, 110 and 118. Now when we mark this as free, we say that this is 1. So now in our pool of memory, this is the process's pool of memory, right? This is the process pool, memory pool. So now what we have in our pool is we have one free block of size 4 bytes and it's free. So let's say now what our process wants a 2 byte block, right? It needs 2 bytes of memory. As usual, it will call Ymalloc with 2. But this time, instead of directly going to sbrk, it will first check the entire memory pool. Does it have a 2 byte block free? So it will start checking from here. Like it first checks this block. Is it free? It's not free. This block, is it free? Yes, it's free. But what is its size? Its size is 4, but no other block is free, right? And this is the first free block it's getting. and it kind of satisfies its demand, because although it needs 2 bytes, but we have 4 bytes free, so the 2 byte request can be satisfied by this 4 byte of block. So instead of calling sbrk again, it will return the address of this block to the process. It will return the address of this block to the process, and it will once again mark it as occupied, right? So now, so that the process can now use this block. Okay, so let's try just one another example to understand. So before trying another example, this approach that we took, like we scanned the pool of memory from the first block, and the first empty block that we found which could satisfy our demand, we used that block. We basically reused that block. So this strategy is known as first fit, because we are choosing the first available large enough block to satisfy our memory requirement. So let's see another example of this first fit strategy. Let's simulate a memory pool. So let's say all these blocks, like 1 block, 2, 3, 4. Let's go with 5 blocks, and let's say all these blocks have been allocated via sbrk by calling Ymalloc again and again with different memory sizes. Let's say the first block we have is a 4 byte block. It is being used. Another 8 byte block, it is being used. Another 2 byte block, again it's being used. Then let's say 16 byte, and we have another maybe 4 byte, and also it is being used. So what happens now during the lifetime of the process is, the process, let's say, doesn't require this 16 byte block anymore. So this 16 byte block is now empty, and again this 4 byte block is also now, sorry, this 16 byte block is now no more required. It's now reusable, and this 4 byte block is also now reusable. And let's say now another request comes for a Ymalloc of, let's say, 2 byte, right? We want a memory allocation request of 2 byte. So in this first fit strategy that we just discussed now, the scanning will once again start from the beginning of the memory pool, and if we want, we can once again name the addresses. It's 100, 104, 112, 114, 130, 134. So it starts from here. It wants 2 byte. So we first check for this block. 4 is greater than 2, but this is occupied. This is in use. 8 is of course greater than 2. This is occupied, but this is being used. 2 is exact match. This would have been our best choice, but this is once again being used. 16, this block, the 100, the block which starts at 114th, this is not used right now. This can be reused. Basically this block has been freed. So this is the first block that our scanner will find, which is free to be used, and the size of the block is large enough to accommodate 2 byte. So this is the block that our scanner will return to our process. Now one interesting thing here is 4 would have been a better choice. The 4 byte block would have been a better choice, because in this case 4 minus 2, because 2 is what we are requesting for, remaining 2 byte would have been wasted, because the demand is only for 2 byte. But we would have done a way lesser wastage if we would have chosen this 4 byte, if we could have got this 4 byte block, or this would have been the best one. Like, and also this 4 byte block is free now, free to be used. The first fit approach says that get whatever block you find first which satisfies the request and which is free to be used, that which has been freed. So in this case we get a block whose size is 16, and 16 minus 2, 14 bytes goes to wastage. So this is also known as internal fragmentation in memory, because we get back this block, but internally 14 bytes is going to wastage, because we don't need more than 2 byte at this point. This is one strategy, and this strategy is called first fit strategy. The next very common and trivial allocation strategy that we have is the best fit. And as the name suggests, in best fit, we never get satisfied with the first free block we find, but we scan the entire memory pool and we try to find out which is the free block whose size is nearest to the size that we demand, so that the wastage is as minimum as possible. Okay, so let's take another example. This is the current allocations that we have is once again 5, and this is 4, this is occupied, this is again 8, this is occupied, this is again 4, this is occupied, 16, and let's say 8. Let's make it 2, and this is occupied. Now what happens is, let's say the second block becomes free and the last block also becomes free, like free to be reused. 1 1. And now let's say I want a new allocation. Let's make this one something like 4. Let's make this 4, not 2 but 4. So now what we are looking at is we want a new allocation of something like 2 byte. So we make a Ymalloc call with 2, right? So once again the scanning will start from here, from first, and it will check each and every block. So if you see, if we check from here now, the first free block which can satisfy our demand of 2 bytes is this block. This block here. This has got 8 bytes, right? But it won't stop here. It will still keep on scanning. Like it will come to here. This is sadly this is used. This will come to here, then this is also used. Then it will come here, and this is free. So now it will check like its size is greater than 2. It is a block with the size nearest to that of our demand of 2 bytes. Because 4 minus 2 is 2 bytes, 8 minus 2 is 6 bytes. This is the block with the size closest to the size of the block we are looking for, which is 2 bytes. So it will choose this. So it will make this 0 and it will return this block to the process. So this is the best fit approach. Similarly, we have other various approaches. Like we also have an approach where we try to split the block, right? We try to split the block and we create new block, and accordingly we do the allocations. For this video I won't be going into the splitting of the blocks and the other advanced memory allocation strategies like the body allocator, which I'll just mention briefly. I'll just stick to first fit and best fit. But what essentially happens in split is, I'll just show with an example. Okay, so what happens in splitting strategy is, let's say you have this, let's say 3 allocations of 8, 4, and let's say again 8. And now let's say this first 8 becomes free and other 2 are occupied. So now what happens is I call Ymalloc with 2. So basically I want a memory block of 2 bytes size, but the only block I have free is that of an 8 byte. So with best fit or first fit, in this case I would have written this block of the first block of size 8 bytes. But however, with the splitting strategy, what we would do is we would split this block. So we would split this block, and this would become a block of 6 byte and this would become a block of 2 byte. Again, I am hiding some of the splitting details. It is not as trivial as what I'm showing over here, but I am just abstracting some of the internal implementational details. So what happens is that I'll divide this block, I'll split 2 block out of this, and now we have 2 blocks. One block of size 2 bytes and one of size 6 bytes. So this 6 still remains free, but this, it will be marked as not free, f equal to 0, and this will be returned. So this is splitting. Now what happens when this 2 bytes block is no more required? That is, this becomes free. What would happen then? Then we would do a merge. So then basically we would remove this partition, and this would once again become a single block. We would make it back to a 8 byte block, right? So why we do the merging? Why is merging necessary? Had it been still partitioned into 2 and 8, right? Had it been still partitioned into 2 and had it been still partitioned into 2 and 6, now both this block is free. Because we partitioned, we chunked out our 2 byte block, and now the work of this 2 byte block is finished, so it was freed. So if we have 2 such separate blocks of 2 and 6, total 8 byte, but partitioned, the problem with that is external fragmentation. That is, let's say now a request of 8 bytes come. we won't be able to satisfy this request with this arrangement right now, because this 8 byte block is occupied and we don't have any other 8 byte block, but we have a 2 byte block and we have a 6 byte block which is next to one another. Both of them are free, but we won't be able to satisfy it because it's split, it's partitioned. So this is something which is called external fragmentation, right? So we need to defragment this memory, and for that we will simply merge it. We will remove this, we will break this boundary, and we will merge it into 8 byte block, and that is defragmentation. Let's try to understand how can we implement this concept or this strategy of just best fit and first fit, and the concept of this entire pool of memory and blocks, and the concept of freeing and allocating block in our pool of memory using C code or using the data structures that are known to us, right? So let's have a look at that. Once again, let's take an example, and let's go with 4 blocks this time. Let's say this is 4 byte, 8 byte, 4 byte, 2 byte. Okay, and these are just our allocation right now. I'm not writing f equal to 0, f equal to 0 again. It's assumed that all of these are occupied right now. So how can we represent this? That is, how can we represent this pool of a memory, these blocks one after the other, and most importantly, the metadata of the block. By metadata, I mean what is the size of the block, what's the next block after a certain block, and whether it's free or not free. That is our F flag or our free flag, right? And here comes the linked list data structure to our rescue. So we can represent this entire dynamic pool of memory using a linked list. So we will use linked list to represent each block of this memory and which block is located after which block. So that relation as well. Not only that, we need to define some other metadata as well for each and every block, right? We also call it as block header. And what kind of metadata are we talking about? We are talking about things like whether the block is free or not. That is our free flag. What is the size of the block? The most important thing. How do we know what is the size of a block? We need to maintain that as well. And which block comes after the given block? Basically the next pointer of a linked list. So all this information about this block of memory in our pool is the metadata of the block. And what we will do is we will try to smartly piggyback this information into this block itself. So we will use, because this data also needs some memory to be stored, right? And we will piggyback this memory out of the given memory block. So each block will have a header section, right? So this is the header section which will have all this data. So what essentially this will have? This will have things like whether it's free, like a variable to indicate that 0 or 1. The size, it can be just a size t variable, size t size. We will have the next pointer, whose type will be pretty much the type which we will use to store the header, right? It will be just a struct. And optionally, we can also have a variable, a marker variable. We can use this for debugging purpose for our toy allocator, which will say that how this block was allocated, whether this block was directly allocated from the system via sbrk, whether it has been just now allocated by sbrk from the OS, or whether it's a reallocation. That is, we are using some already existing freed block. We can also store that. I mean, this has got nothing to do with the implementation of the strategies, but this is just for our own debugging, right? And we will entirely piggyback this in this block of memory, which brings to a very interesting point. This means, so our block comprises of the header, and then comes the data, the actual block, the actual area where the data will be stored. So when our scanner or our allocator returns the block's address, we will need to be very careful, and we need to send the pointer which points to the beginning of the data part and not the header part, because the process has got nothing to do with this header. It's only required by the allocator to maintain the allocations and the pool. Like, the process doesn't need to know about this header. When we have chosen a block to reallocate, we will have to manipulate the pointer in such a way that it returns the address of this data portion of the block, beginning of the data portion of the block, and not the header. We need to ignore this header. And this also means, let's say size header represents the size of the header struct, right? This also means that when we are requesting for a certain amount of data, certain amount of bytes, let's say x, where x can be 4, 8, 16, anything, we can't just ask the OS for that much amount of bytes. Why? Because we need to account for this header size as well. So whenever the user or the process requests for X bytes of memory, we will actually request for X plus size of header, this much amount of memory. Why? Because we need this extra size to piggyback the metadata into the same block. That's why we will never use sbrk with the actual X, that is the number of bytes wanted by the process, but X plus size of header. So these two things we need to keep in mind. And rest is, it becomes very easy to do with just usual pointer arithmetic and linked list, because each block of the linked list will have the data section, the header section will have next, and each header's next will point to the next block's header, right? Similarly, this header will point to this block's header, and so on. So it's a classic linked list. We are using a classic linked list to use as a core data structure to create our memory allocator and to store our blocks. And one small but important nuance that's remaining is, if we find out a block, how do we send the pointer to the data part to the process instead of this address of the beginning of the block? Okay, so finally, this brings us to the question, how can we set up our block, right? And once we know how to set up our block, we will also know how to get to the point from where the data starts. It's just a matter of pointer manipulation. So for that, let me use this area to explain that. So first we need we need to request some memory from the OS, and let's say we call the struct that defines the header metadata as header underscore t. We can simply type def the struct to something called header t. So now, while requesting memory from the OS, what we can simply do is block equal to sbrk, x is whatever amount of memory we want, plus size of header t. It's just pseudocode. I am not going for the exact C syntax, but yeah. So what this returns now, in this case, sbrk returns nothing but a void star pointer, right? So block is nothing but a void star pointer. What we can do is, we need to typecast, or we need to get access to the header part of the block. For that, we can simply do h equal to, we can cast this block as header underscore t block. So from pointer arithmetic, or from basic pointers, what we know is that this will try to typecast, or this will try to cast this amount of memory, this raw amount of raw memory that we got, that is block, into segments of memory, where each segment is of type header t, right? Basically, that's what we usually do when we allocate an array, right? Let's say when we are allocating a character array, or let's say when we are allocating a integer array of, let's say, 4 integers, we ask malloc to give us size of int into 4 amount of memory. Once we get that, what we do is we typecast that block of memory into int star. So what that essentially means is, we now got back a array of integers of size 4, because we did 4 into size of int. Let's say size of int is 32 bits or 4 bytes. So now what happens is, basically typecasting a region of memory by some pointer type, it converts that memory into segments of that data type, what we are looking for, like int in that case. So in this case, similarly, block, the free region of memory, that is block, it will be typecasted into segments of header t data types. So what h will denote now is the first such segment of this entire block. So this basically means is that this first segment will be typecasted to a header t type. Now if we do a h plus 1, we will simply go to the next part, right? It is like the next segment which will be typecasted as a header, right? And so on. We can do h plus 1, h plus 2. Similarly, in case of an array, if we have done an int star on a block of memory, and let's say the name of the array is a, then a will give the 0th element of the array, the 0th int. A plus 1 will give the second element, a plus 2 will give the third element. Even here, we can keep doing h plus 1, h plus 2. We will go to the second segment, which will be treated as type header, then the third segment, which will also be treated as type header, and so on, because our pointer type is header t. It's that simple. So once we have this header, we will set it up. We will fill up all the values, like we will fill up the free value, the next value. Again, filling up the next value is simply adding a node to the end of the linked list or to the beginning of the linked list. It's normal linked list operation, and that's the beauty of this entire procedure. And then also we will fill up the, what else, the size, the very important variable. We will fill up the size as well, and then we will simply return void star h plus 1, right? We will simply return this. What this essentially does, h plus 1 will go to the next segment and make it treat as a header type, but we don't want it to be treated as header type, right? So we will once again typecast it back to void star. So now once again, this from here, basically we return the portion of the block which comes just after the header area, and we typecast it back to void star. So this entire chunk of memory will be returned, and this will be returned as a void star pointer. So that's just some usual pointer arithmetic there, very smart pointer arithmetic there, with which we can make sure that we are returning the part of the memory block that the process will be able to use as a block to store data in it, right? So that's how we can model this entire allocation, deallocation. And again, simply free is nothing but, once we have the allocated block, we can simply go back to the beginning of the block using, once again, using pointer arithmetic. Here we are doing h plus 1, then we will do h minus 1. We will go, h minus 1 will give us the starting of the block, and we can simply once again set the various metadata, like we can make it free, that free equal to 1. We will mostly update the free flag to mark that it can be used now. And this much knowledge which we have gained should be enough to let us implement an end-to-end memory allocator in C using linked list and this pointer arithmetic, and we'll see next how we can do that. So now let's create our memory allocator. So the first strategy we'll be using to create our memory allocator is the first fit strategy, and once we have done that, then we will do some optimization, and then we will move on to adding the second strategy, that is best fit strategy, right? And then we will use some sort of flag to choose a strategy on demand in order to do our memory allocation. So let's get started with creating our memory allocator. So the first thing I'll do is, I just have a blank directory right now, and the first thing I'll do is I'll create a makefile, and let's populate the makefile. So I'll have a build recipe, which will be just simply gcc -o ymalloc.c. It will just simply compile it. Then we will have a run, which will simply run it. We'll have a build and run to just shorten the process. Build and run, and we will be writing a test file as well, a test suite as well, a very simple test suite, no external libraries, just normal. So what we will do is, we will create a tests.c. It's nothing but a usual program. Instead of using malloc to allocate memory, we will be using our own replacement of malloc to allocate memory, right? So that's pretty interesting. It's always fun to know how the internals of these library calls or these system calls work. And it's even more interesting when you realize that you are replacing something which has been provided to you, which everyone uses out of the box. You are replacing it with your own implementation. It might be not as efficient as the malloc's own implementation. Of course, it won't be. Malloc, sbrk, these have been developed over several years, with so much of expertise has gone into it. But it's always great to learn this kind of things, how it works and how they work internally. Okay, so so I'll compile it, run the test, and I'll just delete the compiled file just to clean things up. So that's a tiny makefile. Next, let's create main.c. Actually, not main.c, but let's name it malloc.c. ymalloc.c. Yeah. Okay, so first, as usual, I'll start with some header includes. Let's define some macros to, remember, we'll be using a sort of, let me go back to the design. So remember, we decided to use some marker to know what kind of allocation this block has gone through, like whether it's a freshly allocated block from the OS or it's a reallocated block from our pool, like that, or it has just been freed, like it was previously in use but now it has been freed. So in order to use those kind of marker, we will define some constants in form of macros. Let's do that. Okay, so now as usual we will just define a exit with error macro. It always comes handy. Okay, that's our tiny error display macro. So let's start with creating our block header type, and how our memory block header will look like. The header will store all the metadata of the memory block, like the size, whether it's free or not, all the things that we discussed. So let's do a type def struct mem block header size underscore t block size, and I'm using size t because that's sufficient in this case. The size of size t is usually platform dependent, and it depends on the type of system and the architecture you are using. So on a 32-bit system, size t size is usually 32 bits, like that is 4 bytes, and on a 64-bit system it is 64-bit, that is 8 bytes. It's very different from your assembly word, which is usually 16 bits or 2 bytes, like how we have word, dword and qword on assembly. That's different from this one. This is more of like, it depends on the CPU architecture you are running, whether it's a 32-bit CPU or a 64-bit CPU. So then we will define free, then we will define the marker, we'll call it magic. Then we will define the pointer, which will point to the next block, right? That's very important. That's how we'll create our linked list. So this is basically the link of the linked list, and let's call it block header t. That is our type. Let's define a constant which will refer to the size of this header block, or this block header, and that will be, let's call it block header size of block header t. And now one of the very important thing are the block which will denote our linked list, right? So every linked list has a header node, right? So this will be the header node or head node of our memory pool linked list. So this is our memory pool. It's basically a linked list of the memory blocks, that is the actual memory block plus the header information, and this is like the mem pool is the head, the linked list head, the head node. Okay, so first things first, let's define a function which will request some memory from OS, and of course it will return a type block header t, because we will piggyback the header information in the block as well. So the name of the function will be get space from OS size t size block header type star block equal to sbrk 0. So right now block is pointing to the current program break, right? It is pointing to the current program break in memory. And now what we are going to do is we are going to request some memory from the OS, and now we will send the actual size that we want to request from the OS, plus we need to add header size to it. So here our header size macro will come handy, right? And simply we'll see if block request equal to void star -1. So in case sbrk could not get memory from the OS, it returns -1 typecasted to void star, and if that's the case we will return null. Now block was already pointing to our previous program break, and so remember sbrk changes the program break returns a pointer to the beginning of the newly allocated memory region, right? So block is pointing to the beginning of this memory region. So what we are going to do is we will piggyback the header information into block. Basically, irrespective of the size, what we have done is the memory is right now typecasted to the entire chunk that we are getting back here is typecasted to segments of blocks of type block header type, right? So we'll just piggyback the header information to the beginning of the entire block that we got back. Block dot block size equal to size. We need to track the size. We will make it occupied because it has been demanded by the process. We know the process is going to use it, of course, after adding it to the pool. Next, we will take care of it later, and we will put block.magic equal to new alloc because it's a newly allocated, fresh newly allocated block provided by the OS, and then we'll simply return. So next, what we will do is we will write a function which will find us a free block from our memory pool using the first fit strategy, and you'll soon see it's extremely simple to do that. We already know theoretically that it's easy. Now we'll see practically that it's indeed easy. Star find free block first fit, and of course we need the size, like what size we are looking for. So we will create a temp node of type block header t, which will point to the beginning of the mempool head node, and this is very similar to what we would have done to traverse a linked list. We never change the head node. If the head node is gone, the entire start of the linked list is just gone. So what we do usually is we allocate a temporary node, we point it to the head node, and then we do the traversal, right? So we'll do exactly the same thing. So whatever basic concepts we know about linked list, a classic linked list, we'll be using exactly those to create this allocator. So we'll point to mempool, and then what we'll do is while cur not equal to null, that is we haven't reached the end, and not cur dot free equal to 1 until we reach a free node whose size is greater than equal to the demanded size. We will simply keep going forward. We'll skip the node. We'll keep skipping the node until we find a free block whose size is greater than equal to the size we need. And once we have found it, we simply return the address of that particular node, or basically pointer to that node. So that's it. That's our find free block first fit function, which finds us a free block using the first fit strategy from our pool. And now using these two functions, what we will do, actually we need one more function. Let's say you have got a node from the OS. What do we do next? The immediately next thing we do is we add it to our pool of memory, right? And before sending it to the process, the requesting process, we add it to the pool of memory at the end of our memory pool actually. So let's do that quickly, and it's exactly same as adding a node to the end of a linked list. So let's do that. Add block to pool block header t, and this is the new block that we are going to add. So we'll check if the memory pool is uninitialized, that is there has been not a single block added to it, that is not even a single block has been added to the pool, then it's the easiest case. If it's empty, then we simply initialize it with our new block, as simple as that, and return. If not, then we do the classic addition of a node to the end of a linked list. So until we reach a node whose next is null, we keep on traversing the linked list, because the last node is the node that we want. Once we have reached the last node, we simply do cur.next equal to block, and that's how we add a block to the end of a linked list, and we return. So that's our tiny at block to pool function. And finally comes our void Ymalloc, which is our version of malloc, and what it takes is a size. Once again, first things first, we do a smoke test. If size is less than equal to 0, we simply return null. We declare a block and make it null. Okay, so now the first thing we will try to do is try to find a free block from our memory pool. So block equal to find free block first fit, and we will send the size. And if block is not equal to null, it means we did find a free block from our pool, and we will prepare it to be sent back to the process, the requesting process. So first we will do free equal to 0 because it's no more free. We will do block.magic equal to realloc, and we will return void star. Remember, the header information is only at the beginning of the block, so we will use pointer arithmetic to just go beyond that header block, and whatever exists beyond that header block, thus we will just typecast it to void star, right? So that the process returns a void star pointer to the allocated memory block, and it can typecast it to whatever it needs that block to be, right? Whatever data type it wants it to be. And yeah, so that's the case when we have a free block in the pool. But if we don't have, what do? We request from the OS. If block equal to null, that is, for some reason the OS could not allocate us memory, then we simply return null. After we have done that, what we do is we add this block to the pool, as we mentioned we will do, and we send this newly allocated block to this function, and once again we send void star block +1, and that's it. That's our memory allocator, which uses first fit strategy. So what we did here, we did if size is less than equal to 0, we simply return null. Then we created a placeholder block, we declared a block, and we tried to fetch a free block of our desired size from the pool. If it was not null, that means we got a valid block, we set it as free, we mark it as a reallocated block, and we return block +1 typecasted to void pointer. Next, if we were not successful getting a free block from the pool, what we do is we request some space from the OS, and if that was also unsuccessful, we return null, or else we add the newly allocated block to our pool and we return block +1 typecasted to void, right? So that's that. We now need to implement another thing which is provided by every allocator, that is free. So in order to free a block, the free function call will be called with the actual memory block, not the memory block with the header. So the starting point will be the raw memory block which was used by the process to store data, right? In order to free the block, we need its header information, right? For that, need to come up with a mechanism using which, given a data block, given the actual data block, we can navigate our way to the header of that block, right? And that is again very easy. We just need to typecast it to block header type and go one segment back, rather than going one segment forward, which we are doing right now. We need to go one segment back. Just the reverse of this. Let's do that. So we'll call it get header, header, get header from data block, and it's void start data block. So this data block is basically this, that is block plus 1, right? We are simply typecasting it to void star. So we'll just do the reverse of this. So we will do return. First we will typecast it to header t, of course header t star, and we will do data block and -1, as simple as that. So we'll go back one block header t pointer, and now we can easily create our free function. Let's start data block. If data block was called with null, what we do is we return. We can't do anything. Next, block header t star block equal to get header. We will use this newly defined function and we will send it data block. Now we will free it. We'll just do a sanity check. If for some reason that block is already free, we don't need to free it again. We will simply return. If not, these are once again some sanity check. If block.magic, if not block.magic equal to new alloc, or block.magic equal to realloc, that is, it's not, this block was not created by us like our allocator. If somehow this condition satisfies, we return, because it means it was not created by us. If none of these conditions are true, then what we do is we free the block and we set magic to freed, right? So that's how we can free a block. So that's a very tiny basic end-to-end allocator, right? And now we can actually use this in a program to allocate memory to our process. Okay, so now that we have our first version of memory allocator, let's write a tiny test file. The test file is nothing but a simple program which uses this version of malloc, that is Ymalloc, instead of the normal malloc. That's how we will test it out. For that, the first thing we'll do is we'll create a header file so that the other programs are able to use it. Do unis td.h here. I'll import unis td.h here, and then I'll just declare two function declarations or function signatures. One is ymalloc, and the other one is free. That's it. And now we will define our tests.c file. So now we will include assert.h. This will help us to do quick assertions, and we will do ymalloc.h. We will include ymalloc.h. So the first test we will write is void test new allocation from OS. This is when we have just started our program. There has been no past allocation, so our memory pool is pretty much empty, and now we will try to allocate some memory in this situation. So in star num equal to ymalloc size of int. So basically I'm asking for 4 bytes since it's a int type, and that's it. And now what I want to assert is like this is not equal to null, and after that I'm going to free num. The next test I'm going to do is I will do a void test reuse single block. And remember, since this is a single program where each test case is simply a different function, remember that our memory pool is never reinitialized, right? So our memory pool is the same memory pool for across all the functions. So whatever allocations we make here will be persisted across all the functions. So that we need to keep in mind while writing these tests. Ymalloc size of int, and what we want to assert before moving further is num1 is not equal to null, and then we free num, and now we do another assertion, num2 we do size of int, and what we should expect is num1 equal to num2, and then we just free num2 as well. Why this should be equal? So let's consider we are running this as the first function. So what ideally happens is that on the first Ymalloc, the request goes to OS because right now the memory pool is empty, right? So we get back a block of 32-bit, right? And then we immediately free that memory block. So this time it's in our memory pool, but its state is free, right? Now in the second case, we once again want to Ymalloc same a block whose size is that of a int variable. So once again we want to dynamically allocate a 32-bit memory block, and this time the request should not go to OS, rather we should reuse the initially freed block which is existing in our memory pool, right? So ideally that should be happening according to the logic we have written in Ymalloc. So that's why this num1 and num2 should be the exactly same memory location, right? And hence we do assert num1 equal to num2. If it's not the same, then there is some issue with our memory allocator. And now let's write one last test for first fit. Here we make sure that the first fit algorithm is working properly. That is, we get the first block in the memory pool whose size is large enough to accommodate our requested memory, right? So let's do that. Star num1 equal to Ymalloc size of int. What we do next is assert num1 not equal to null, then we Ymalloc Ymalloc 3 into 4 bytes of memory, because size of int is around 4 bytes into 3, that is around 12 bytes of we Ymalloc 12 bytes of memory. And yeah, and then of course let's assert that num2 not equal to null, and then we do Ymalloc size of int into 2, and once again we assert that num3 is not equal to null, and then what we do is we free both num2 and we free num3. So technically now we have two freed blocks in our memory pool, one of size 12 bytes and the other of size 8 bytes, right? So now what we do is we try to allocate another memory block of size 4 bytes. And technically what should have happened now is we should have got back the block which is of size 12 bytes. Why? Because we first allocated a memory block of size 4, then 12, and then 8. So technically, if the first fit algorithm is followed, since both of these blocks are free, the first free block it will hit while scanning the memory pool is this one, and the size of this block is large enough, that is 12 bytes, it's large enough to accommodate a memory block request of 4 bytes, right? So what we should see is num4 equal to num2. This should pass, and then we simply free num4. So now let's try to compile our code. So actually I did one error over here. We won't be able to compile ymalloc.c in this way because it will try to produce an ELF executable file, and in this case it would fail to do so because there is no main function in ymalloc.c. So instead what we can do is we can simply do gcc-c, and this is basically of no use because we won't be using this as a runnable program or as an executable program. So we'll just remove these. So what I want to do, my only intention of trying to compile this is to make sure that we don't have any syntactical error or something like that. So we will just do a make build. It will be actually -o and -c. I believe this should work, and it worked. So we got Ymalloc created, which means it works fine. Let's quickly write a clean function as well, where we just get rid of Ymalloc, so that we can simply do clean, and others, yeah, okay. So now what we are going to do is we are going to run our tests, and before we do that, what we need to do is we need to write our main function, and here what we can do is we can simply call all of these methods one after the other. Actually, to keep things proper and to not run into any unwanted errors or any unwanted situation, what I would prefer doing is, ideally I should have used a proper test suite, but maybe from next videos, if I want to do something like this, I would use a proper C test suite, which spawns different processes, maybe something like that. But in this case, I'll just run these functions one off, and let's see if it works. So this is the most basic case where we are able to request some memory from the OS, and let's do that. Make test, and it passed, right? It passed. Num was not equal to null, so at least our sbrk worked as expected. Now let's remove this and let's try this one. This passed as well. For example, we could have done something like this just to make a failure situation, and it would have passed. So means our tests are working, and it also means our memory allocator is working as expected. So we were able to free a block and get back that block on the second allocation, so we could reuse our block. Now let's test that our first fit algorithm is working fine, and it is working fine because num4 is indeed equal to num2, because we got back the first block that could satisfy the request. Doesn't matter if it is the best fit or not, we just got back the first free block. Now that is our first fit strategy implemented, and we have got a very basic dynamic memory allocator in pretty much 100 lines of code. So now we can optimize our code further. So we don't actually need this method add block to pool, because what we are doing here is pretty similar to what we are doing here. The reason I say this is, so at add block to pool, we are traversing the memory pool till the very end, right? We are traversing it till very end, and then we are adding the new block to the next field of the last existing block of the pool. So basically we are traversing to the last existing block in our memory pool, and we are doing node.next equal to new block, that kind of thing, like typical addition to the end of a linked list. But if you see, here also we are doing the same thing. Like in this case, in case of a negative case wherein there is no free block in our memory pool, we are traversing the entire linked list until we are reaching the last block. Actually not the last block, but the next. We are doing a cur equal to cur.next even on the last block, which is actually making cur null, because the next property of the last node in a linked list is always null, right? So what we need to do is we need to keep track of the last node in the existing memory pool, and somehow we can transfer or we can send back that reference to the last node, or basically somehow we can return the pointer to the last node back to this Ymalloc function. Then our purpose is kind of solved, because if we have the last existing node in the memory pool, we can simply do a last node.next equal to new block from Ymalloc itself. We don't need to traverse the entire linked list once again in add block to pool. But the problem is we are already returning this return cur, like the actual memory node from this function. It can be a free block or it can be null, And we know that in C we can always return only one value from a function, right? So somehow we need to return the pointer to the existing last node of the memory pool as well. And for that purpose we can take help of double pointer. So what we can technically do here is we can send this function another parameter called last, and it's a double pointer, which means it's a pointer to a pointer. And what we can simply do is at every iteration we can set last like star last, as in the value at star star last, which is also a pointer. We can set it to cur, and that solves our purpose. So the last pointer will keep on getting updated to the value of cur. And since we are using a double pointer, we don't have to return anything. We can initialize this last pointer here. In a moment I'll show you what I'm trying to achieve or how I am doing this. So what I'm going to do is I'm going to slightly tweak this. I'm going to do a base case here. If that is, I don't want to go till the first fit allocation strategy or any allocation strategy at all if my memory pool is empty right now, because it makes no sense. If memory pool is empty, it means there is no free block in my, there cannot be any free block in my memory, and so I have to request memory from the OS. So get space from OS size if block equal to null. We simply return null for obvious reasons, because the OS could not provide us with any memory block. And then we simply initialize the memory pool with block, and then I return void star block plus 1. Cool. Now what I do is I now define this last variable or last pointer. I now define this last pointer and I point it to the beginning of the memory pool linked list. Basically I'm pointing it to the head node, and what I'll do is I will send a reference that is a pointer to this pointer, or rather than the address of this pointer, right? So I'll try to explain in very short why a double pointer is required here and why a single pointer can't work. Because a single pointer would work when we are trying to return multiple values from a given function, right? We can simply use the value at operator, that is a star operator, to update the value of the memory location being pointed by a pointer. But in this case we don't want to get back a value from the function, we want to get back the memory pointer, right? And since we want to get back a memory pointer, we need to use a pointer to a pointer, because the pointer itself, when you send a pointer from one function to the other, the value at that memory location might not change or it remains unaffected. That's why we call it a copy by reference and not copy by value. But the memory pointer, the pointer itself is copied by value, it is not copied by reference. So often we think that whenever we are using pointer, we are doing a copy by reference and not copy by value, but that's not correct. The value of the pointer is being copied by reference, but the pointer itself is being copied by value. So I'll try to create a separate video on this or explain this concept with a bit more clarity, taking my own time. But as of now, what we need to know is we cannot use a single pointer here to get back the last node pointer, but we need to use a pointer to a pointer, that is a double pointer. So far so good. And now what we do is we simply check if block not equal to null. If block is not null, that means we got a free block from the pool, which is great. Then we set it up. Otherwise we get space from the OS. We check if it's null. If it's null, again we can't do much. Otherwise, instead of calling this function, we do a last dot next equal to block, and that's so cool. We were able to eliminate an entire function of adding a node to the end of the linked list just by keeping track of the last to which we traversed while trying to find a free node in our memory pool. So what we can do is now we can simply get rid of this function. We don't need it anymore. So once again what we did here is pretty much we created a temp block. If mempool is null, we initialize mempool with the block we get back from OS. If OS returns us null, then we can't do much. We simply return null, or else we initialize mempool with the block. Otherwise, we set up a pointer called last, and while finding our first free block, we send a pointer to last as well, and the size, the amount of memory we want. If we get something tangible from our memory pool, we use it and we return that, or else we get new space from OS and we set the next value of last to the block to add it to the end of our memory pool as a new node, newly acquired memory block from the OS. So that's that. And now let's test it once again. Let's test use single block, and let's do make test, and it works, which is great. Nothing broke, so there is no regression. Okay, so now the next thing we are going to do is implement best fit. So that's the next strategy we are going to implement. So that would be also pretty easy, but before that I want to just change our function definitions a bit so that we can pass. What I want to do is I want to customize this Ymalloc a bit, for which I'll change its signature. I won't follow the classic malloc signature anymore, but I want to accept a flag as well, which will tell me what kind of strategy I want to follow. So let's do that. So for that, the first thing I want to create is an enum, and that enum will pretty much have the values of the type of strategy that I want to use, and I'll define it in ymalloc.h because it will be used by the user program as well as ymalloc, because the user program or the user process is what will determine what kind of strategy it wants to use. So let's do that. So it will be a simple enum. First we will have first fit, and then we will have best fit, and we will call it placement type because after all it's the placement strategy. And now our ymalloc will also accept this placement type variable or parameter. We will add it here as well. We'll call it simply placement. Actually we need to include this file as well, and that should fix this. Yes. And we will create a wrapper function or a generic find free block function, which will take the decision which actual function to call. So what we'll do is we'll create a function called block header t star find free block. So that's a function we will have, and it will accept all the usual parameters, that is block header last size t size and placement t placement. And now we will define null. We will use a switch statement to determine what kind of strategy we want to use. And if it's a first fit, what we do is we use block equal to find free block first fit, because we want to use a first fit strategy, and we send last and size, and then we do a break and we return block. Right, now let's quickly write our best fit strategy. So the function that will implement the best fit strategy. For that, once again we will we'll name the function as block find free block best fit block header star last size underscore t size cur equal to mempool. Once again, this is our temp pointer for traversing, and we will have another block which will hold the actual block this time, which we will return, and that is null. And this should be block header t, and while cur not equal to null, while we haven't reached the end of the linked list, once again we store cur in last, and if cur dot free equal to 1, that is the node is free, and cur dot block size greater than equal to size. So what the condition is same as first fit, and now the change happens. What we do is and block equal to null, which means this is the first block in the linked list. There is a head node, so we don't have a reference point yet. Or cur. So remember we are using block to store the last preferred block. So this block we have defined, it's used to store the last block we have selected, right? In best fit, what happens is that we keep on traversing until we find the block with the smallest size which can satisfy our request, such that internal fragmentation is least. So and then block equal to null. So if block is null, we haven't seen any previous block yet, so we'll simply use that. Or else if there is a previous block that we selected, then we'll make sure that current block's size is less than block dot block size. If only this condition satisfies, only then if the current block size is less than the existing or the previously selected block size, only then we will update our selection, otherwise not, right? Because we want the smallest block that can satisfy our request. If that's the case, we simply do a block equal to cur, and we always traverse, for which we do cur equal to cur dot next, and once done we simply return block. And finally we add another case here. If case is best fit, we simply do a block equal to find free block best fit last and size, and we break. Although we couldn't have broken here as well, is the last case anyways, but anyways I'll just leave it there. And now instead of calling this function directly, that is block equal to find free block first fit, what we are going to do is we'll use find free block last size, and we will send the placement as well. That's it. And now we can on demand use a different strategy. We can either go for first fit or go for best fit. So now let's quickly write some test cases for best fit. So we are going to write a single test case in order to test our best fit allocation strategy. We don't need to write several test cases here, like only one test should suffice, where we make sure that we are getting the smallest block from our pool which can satisfy our request. So let's do that. And for that, what I'm going to do is I'm going to add a new function here. I'm going to call it test reuse best fit. And before proceeding, what I would like to do, I would send a parameter here, the placement parameter. So these were all our first fit tests. So let's just send the first fit enum. And now, so here as well we will be sending the first fit enum. And finally here. Okay, so now what I'm going to do is, once again I'll make allocation for 4 bytes, that is a int allocation to hold a int data type. So I can simply copy this. I can copy this entire thing actually, and so instead of best fit, now instead of first fit I'll do best fit. So best fit then comes, so first is for one int or 4 bytes, then for 2, then it's size of int into 3, that is 12 bytes, and then finally it's 8 bytes. And now what I'm going to do is I'm going to free num1 once again, free num2, and I'm going to make another allocation of a single int type memory block. So I'll do once again first best fit, and so yep, now I'm just asking for 4 bytes. So earlier what had happened is that we had got back the the block assigned for num2, right? Because it was first fit, even though it was like 12 bytes. So technically now what should happen is we should get back num3, because that's the block with the smallest size but just big enough to satisfy this 4 byte request. So let's see. So we will just pull it down here, and actually it will be num2 and 3. I don't want to free num1, and assert num4 equal to num3. That's our assertion. And finally we will free num4. That's it. And now let's see if it works. Oh, before that we'll just comment out this, and we will do a test reuse best fit, and let's see if it works. We'll do a make test, and it worked, which means our best fit allocation strategy worked fine, right? So if we would have done a 2 here, it would have failed, but we did this. So that's pretty cool. So our best fit allocation strategy is working as well. These are all just test cases to make sure that allocation strategies is working fine. So let's use it to, like a final test case, just to show that we are able to use the memory block return. So it's more of a smoke test, right? So we will now try to use Ymalloc just as a replacement of malloc. So let's see. So in order to do that, what I would want to do is I would want to allocate an array, and in that array I'm going to populate some values, and then I'm just going to print those values, and the array I will be allocating using Ymalloc. So it will be pretty trivial, but I just want to make sure that I'm able to use the data blocks, the memory blocks that I'm getting back, right? And this would be a nice smoke test to confirm that. So I'll call it arrays, and what I'm going to do is I'm going to do star arrays equal to int star. We need to typecast the void star memory that we are getting back, just like we do for malloc, and we'll use Ymalloc size of int into 10, and I'll be using best fit. And now I'll simply go for size t I equal to 0, I less than 10, I plus plus, and I will put. So what I'll do is I'll simply square the values, square the index, and store it in that index position in the array. So this will be enough to prove that we are actually able to store things in the memory block returned. And now I'll simply once again go over the array, and I'm going to print them. Printf and yeah, so I'm going to print it value at I or the index is another value, okay, and a new line. I'll call it I and array of I. That's it. And now I'll comment it out because our testing is done, and I'm going to call this function, and let's see what happens. And it worked. We were able to store values in the memory blocks which were returned by our own implementation of allocator, of our memory allocator, rather than malloc. I believe we had a warning as well. Let's see, what was that warning about? Oh, okay, let's just use int here, and that should be fine. Yep, that's without any warning or any error, and we got our output as expected. We can also play around. We can also use it to allocate a string, and let's typecast it to char star, and then once again I'll do Ymalloc size of char into, I mean, instead of doing size of char you can simply just put a number as well, because char is always, its size is always 1 byte. Yeah, so we can directly put the number. Let's say we put 16, and yeah, that's it. And then what we'll do is we'll do string, let's name it var. Let's just call it var, and I'll do var equal to something, let's say hello. And why is it giving this straight line? Oh, of course, I need to provide the placement strategy or the allocation strategy. And now I'll try to print it. I'll do %s and a new line, and then I'll do var. And it worked. We got hello at the end. So yeah, that was our tiny smoke test to make sure that we are able to use the block, the memory block that we got back, and that's it. We now have a fully functional memory allocator. One thing that we haven't done is, or rather one restriction we have not put is, like, we right now allow any block size, right? It can be 16 byte, it can be 21 byte, it can be 23 byte. Like, we do not take care of what is the number of bytes or what is the size of the block that we are trying to allocate. Ideally it should not be the case. The reason being, it should be word aligned. It should be numbers like 4, 8, 16, 32, like that. It should be word aligned. If you don't do that, what happens is your memory is not aligned and it slows things down, right? So in actual malloc implementation, what happens is that if you ask for a size which is not word aligned or which is not memory aligned, it will give you a block whose size is memory aligned and whose size is closest to the actual size you have requested. So let's say you have asked for something like 5, it will actually give you a block whose size is 8, right? If you ask for something like 3, it will actually give you 4. So like that. So it's always preferred to ask for memory aligned size when you are requesting for a block of memory from the OS, right? That's what is preferred. Otherwise, if you don't do that, you will suffer from performance hit. So that's one detail that we have kind of not implemented here. Overall, this is good enough for a basic memory allocator, and we know how a memory allocator works and how dynamic memory allocation is done, how the memory pool is maintained, and how we can do all of this using nothing but a classic linked list. So yeah, that's what I wanted to share in this video. I wanted to create something useful and actually interesting using just linked list and the system call which I used here, that is sbrk. And in the process, we kind of discussed about how memory allocator works, what are the different strategies and things like that. So let me know if you all like this video, and let me also know that if you all have ever tried creating a memory allocator like this from scratch, and which strategy did you follow. Did you do the splitting of block and all the advanced features that is provided by a modern memory allocator? So let's see, I might do a follow-up video as well after this, where I might actually implement the splitting of blocks and splitting and merger, like split and merger of blocks. So that would be another very interesting and fun thing to implement. But for now, I would leave this memory allocator here with these two strategies. So yep, that was it for this video, and thanks a lot for watching.